Hello student, welcome to my channel The Learn Physics. Today I will be discussing a one-shot video of dual nature of radiation and matter. Now today's discussions are the electron emission, that is waves by which electrons are emitted. Then photoelectric effect and term of photoelectric effect such as work function, threshold frequency, threshold wavelength and stopping potential. Then characteristics of photoelectric effect. Then quantum theory, that is the properties of photon. Einstein explanation of photoelectric effect. Matter wave. Davisson Germer experiment. And finally ncert numericals of all topics. Okay, so today's discussions are very important for you, for your board, NEET, main and advanced. So this video is extremely beneficial for you. Please like, share and comment on this. Now let's start. Now first of all, types of electron emission. First of all, thermionic emission. When a metal surface is heated sufficiently, electron emission takes place from the metal surface. This is known as thermionic emission and the emitted electrons are called thermion. Next, field emission. When an electric field of the order of 10 to the power 8 volt per meter, electrons are emitted from the metal surface. This phenomenon is known as field emission. Now secondary emission. When a high energetic electron strikes on a metal surface, then electron emitted from this metal surface, this is known as the secondary emission. And finally photoelectric emission. If a radiation of suitable frequency incident on this metal surface, then emission of electron takes place. This phenomenon is known as photoelectric emission. Now I will be discussing elaborately on photoelectric emission. Okay, now we have to discuss on photoelectric effect. Look at this. This is a vacuum tube and this is a cathode of low work function. Generally alkali metals like sodium, potassium, cesium, etc. are suitable for photoelectric effect due to their very low work function. This is a metal plate, act as a cathode and this is the anode. Look at this. This is connected to the positive terminal and this is the negative terminal and this is a micro emitter. A radiation of suitable frequency incident on the cathode. Due to incidence of radiation, emission of electron takes place. These emitted electrons are attracted by the anode. So a photoelectric current is passes through it. This current is measured by a microammeter mu A. Now various terms related to the photoelectric effect. First of all, work function. The minimum amount of energy needed to emit an electron from a metal surface is called work function. Its unit is electron volt or joule. The work function of cesium, potassium, sodium are less than 3 electron volt. That is why these metals are suitable for emission of photoelectron. Now threshold frequency nu naught. The minimum frequency of radiation by which emission of electron takes place is called threshold frequency. If h be the Planck's constant, then energy of the photon of frequency nu naught is h nu naught. Therefore, this energy must be equal to work function, which is the minimum amount of energy needed to emit an electron. So look at this, h nu naught, this equal to W. Now W equal to, this is the h nu naught equal to hc by lambda naught, where lambda naught is called threshold wavelength. The threshold wavelength is the maximum value of wavelength of radiation by which emission of electron takes place. Okay, here h is the constant, where h is the Planck's constant and c is the velocity of light in the vacuum. Look at this, hc is equal to, this is the 1242 eV nanometer. Okay, and the value of h, look at this, this is the 6.63 into 10 to the power minus 34 joule second is equal to 4.14 into 10 to the power minus 19 minus 15 electron volt into second. Okay, understood? Now I will be solving some numerical related to work function, threshold frequency and threshold wavelength. Okay, now look at this ncert numerical 11.9. The work function of a metal is 4.2 electron volt. If a radiation of wavelength 330 nanometer incident on this metal surface, will emission of electron takes place. Now we have to calculate lambda naught. If lambda less than lambda naught, then emission takes place. Now we have to calculate lambda naught. We know W is equal to, this is the Hc by lambda naught. Now lambda naught is equal to Hc by W. Now the value of Hc is equal to 1242 eV nanometer. So look at this, this is the 1242 eV nanometer and this is the 4.2 eV. Now eV and eV are cancelled out, so lambda naught, this is equal to 1242 by 4.2 nanometer, this equal to 296 nanometer. Look at this, the wavelength of incident radiation is 330 nanometer and threshold wavelength is 296 nanometer. So emission of electron does not take place. Okay, if lambda less than 296, then emission takes place. Okay, next. Now look at this example 11.2. The work function of cesium is 2.14 electron volt. We have to calculate threshold frequency of cesium. Now look at this, we know the Planck's constant H is equal to 4.14 into 10 to the power minus 15 EVS into second. Now the relation between work function and nu naught is W equal to, this is the H nu naught. So look at this, nu naught is equal to, this is the W by H. Now W is the 2.14 electron volt and this is the, look at this, 4.14 into 10 to the power minus 15 EV into second. Look at this and this cancel out. This equal to 2.14 divided by 4.14 into 10 to the power 15. Okay, this is the hertz. Therefore, this is the 5.16 into 10 to the power 14 hertz is the threshold frequency. Okay, understood? Next. Now stopping potential. Look at this. This is the anode and it is connected to the positive terminal of the battery. And this anode attracts the emitted electron. If the potential of the anode changes from positive to negative, then these electrons are repelled by the anode. At a particular negative voltage of anode, no electron reaches to the anode. That is photoelectric current, that is I equal to N into E equal to 0. This negative voltage at which the photoelectric current is 0 is called stopping potential. The maximum energy of photoelectron which is repelled by the negative potential V0 is equal to E V0. This equal to half mv square. This is the maximum kinetic energy of the photoelectron. Okay. Suppose stopping potential is equal to 0.4 volt. That means the maximum kinetic energy of the photoelectron is equal to, look at this is the half mv square, this is the k max, this equal to E V naught. Now this is the E and V naught is the 0.4 volt. So this is the 0.4 electron volt is the energy of the electron. Now look at this, if it is converted into joule, so this should be multiplied by, this is the 0.4 into 1.6 into 10 to the power minus 19 joule. So look at this is the 0.64 into 10 to the power minus 19 joule. Okay, understood? Next. Now there is a similar type of numerical of ncert 11.3. Look at this here, cutoff voltage is given is 1.5 volt. Cutoff voltage means the negative voltage at the anode by which electric current is 0. So now we have to calculate the maximum kinetic energy of the photoelectron. Look at this here, maximum kinetic energy of the photoelectron K max, this is the E V naught. Now V naught is equal to 1.5 volt, so E into 1.5 volt, so this is the 1.5 electron volt. Okay, understood? Now next. Now the characteristics of photoelectric effect. The rate of emission of electron N is directly proportional to intensity of radiation. Greater the intensity of radiation, greater the rate of emission. Now current I equal to N into E, rate of emission of electron into electronic charge. So here photocurrent I directly proportional to intensity of radiation. Greater the intensity, greater the photocurrent. Okay, understood? Now if a graph is plotted between rate of emission N and intensity of radiation, then this graph is straight line. Okay, now if another graph is drawn here, look at this is the potential difference, this is the photoelectric current for three different intensity, this is the I1, this is the I2, this is the I3. Obviously look at this, here current less, here current more, here current most. So I1 less than I2 less than I3. Okay, and look at this represents the stopping potential V0. This negative voltage represents the stopping potential or cutoff potential. Understood? Next. Now second law, the maximum kinetic energy of photoelectron is independent of intensity of radiation, but depends on nature of radiation and nature of metal surface from where electrons are emitted. So look at this, the maximum kinetic energy is independent of intensity of radiation, is not explained by classical physics. Okay, now a graph. Now look at this graph. We take the three radiation of frequency. Now we take a three radiation of frequency nu1, nu2 and nu3 and have same intensity of radiation. Look at this, if a graph is plotted between along x-axis V and along y-axis I, look at this, the photoelectric current in each case becomes same. Okay, the photoelectric current in each case becomes same. Look at this is the nu1, this is the nu2, this is the nu3. Now stopping potential here V1. So look at this, K1 is EV1. Now stopping potential of this is V2. So K2 is EV2 and this is the V3. So stopping potential, so maximum kinetic energy is EV3. Obviously look at now from here, V1 less than V2 less than V3, so K1 less than K2 less than K3, but all have same intensity. Therefore maximum kinetic energy does not depend on intensity of radiation, it depends on frequency of radiation and the nature of metal surface from where electrons are emitted. Okay. Now, characteristics 3. The minimum frequency of radiation by which electrons are emitted called threshold frequency. No emissions takes place if frequency of incident radiation less than threshold frequency. Okay. Number 4. It is an instantaneous process. It is instantaneous process. There is the time lag between incident of radiation and emission of electron almost zero. Number 5, it is independent of temperature and the velocity of emitted electron ranges from 0 to a maximum value. Okay. Now a recap. Number 1, the rate of radiation directly proportional to intensity of radiation. Kmax depends on nu and work function but independent of intensity of radiation. Now the minimum frequency of radiation by which emission takes place called threshold frequency. And number 4, it is an instantaneous process. Number 5, it is independent of temperature and velocity of emitted electron ranges from 0 to maximum velocity. Now look at this, the characteristics 2, characteristics 3 and characteristics 4 cannot be explained by the classical physics. Now quantum physics. The emission and absorption of radiation is not a continuous process. It occurs in a discrete quanta or packet. The energy in each packet is equal to h nu, where nu is the frequency of radiation and h is Planck's constant. This energy is known as photon. So energy of photon, this is equal to, this is the h nu equal to hc by lambda, and hc this equals to 1242 eV nanometer. Okay, understood? Next, now properties of photon. Look at this, the velocity of photon in vacuum is 3 into 10 to the power 8 meter per second. Okay. The rest mass of the photon is equal to 0 and its dynamic mass is h nu and its dynamic mass m equals to h nu divided by c square. Okay. Now number 3. The energy of photon is equal to h nu, that is hc by lambda, where h is the 1242 eV nanometer and h is the Planck's constant. Now the momentum of photon small p, this equal to h by lambda. Now h divided by, here lambda is the c by nu, so this is the h nu by c. Now h nu is the e, therefore e by c is the momentum, therefore E is the P into C, therefore energy is equal to Pc. Okay. Photon collides elastically with the material particle. Number 6. Now the rate of emission of photon is equal to power of the radiation divided by the energy of each photon. Okay. Energy of photon. Therefore, this is the power divided by h nu. Power divided by h nu. Okay. So greater the power of the radiation, greater. So more the power of the radiation, more number of rate of emission of photon. Okay. Number 7. Photon exert force on a material particle. The force is equal to, this is the power by C for a completely absorbing surface. For a completely reflecting surface, this is the power by C into 2. And last point, the photon exert pressure on the material particle. The pressure is equal to, look at this is the intensity by C for a completely absorbing surface. For a completely reflecting surface, I dash is the I by C into 2. Okay? Now from these properties of photon, what is the nature of the photon? Wave or particle? It is the particle. Now some numerical related to photons property. Now example 11.1. A radiation of frequency 6 into 10 to the power 14 Hz is produced by a laser. The power of the radiation is 2 milliwatt. We have to calculate the energy of photon h nu and number of photon emitted per second. That is power divided by energy of each photon. Now first of all, energy of photon. Look at this, energy of photon equals to h nu. The h is equal to 6.63 into 10 to the power minus 34. So look at this is the 6.63 into 10 to the power minus 34, and this is the 6 into 10 to the power 14. Look at this, 14 and minus 34, so this is the minus 20, and 6 and 6.63, so this is the 40 into 10 to the power minus 20 joule. Okay, now this is the rate of emission of photon per second. So look at this here, power is the 2 into 10 to the power minus 3, and this is the 40 into 10 to the power minus 20. So look at this is the 2 by 40 into 10 to the power 17. So look at this is the 0.05 into 10 to the power 17. So this is the 5 into 10 to the power 15 per second. Okay, understood? Next, now example 11.3. Now look at this, the wavelength of violet light is 390 nanometer. This is the yellow light and this is the red light. We have to calculate the energy of photon of these lights. And if a photoelectric device is produced which is used by the white light, which material you can choose? This is the work function of cesium, 2.14 electron volt. This is the work function of calcium, 2.3 electron volt, and this is the work function of sodium, which is 2.75 electron volt. Now look at this. First of all, energy of photon. Look at this, the energy of photon. This is the hc by lambda 1 of violet light. So look at this is the E1 is equal to hc by lambda 1. Here hc is the 1242 eV nanometer divided by 390 nanometer. So look at this, nanometer cancel out. So this is the 1242 by 390 electron volt. Okay, so this is the 3.2 electron volt. Therefore, look at this, these three substances. Look at this, these three substances have work function less than the energy of the photon of violet light. So look at this, these three substances are used as a cathode for a photoelectric device. Now the energy of photon of yellow light E2 is equal to hc by lambda, so 1242 eV nanometer divided by, this is the 550. Okay, so look at this is the 2.26 electron volt. In this case, the work function of cesium cathode, this is the 2.14 is less than 2.16, so only cesium cathode is suitable for yellow color to make a photoelectric device. Now energy of photon of red color. Look at this is the E3. This is equal to, look at this, 1242 eV nanometer divided by lambda. Lambda is the, look at this is the 760 nanometer. This and this cancel out. This is only 1.64 electron volt. The energy of photon of red color is less than this this and this. So red color is not the suitable radiation for photoelectric emission. Okay, next. Now ncert 11.5. Now energy flux on the earth surface is 1.388 into 10 to the power 3 watt per meter square. Now we have to calculate the rate of photon incident on earth surface per second on 1 square meter. Now look at this. Here intensity of radiation given, here area given. So look at this, the power of the radiation, this is the I into A. So rate of incident of photon, this is the IA by E. Now we have to calculate the energy of the photon E. Look at this, here E equal to hc by lambda. The value of hc is the 1242 eV nanometer divided by wavelength lambda. This is the 550 nanometer. Now look at this, n is equal to IA by E. So here I is equal to 1.388 into 10 to the power 3 into 1, and E is the, look at this is the EV. Here nanometer and cancel out. So this is the E is equal to, this is the 1242 divided by 550 EV. Now EV is converted into joule. So look at this, here 1.6 into 10 to the power minus 19, and unit is rate of incident photon. So this is the per second. Okay, now look at this, here 1.388 into 550 divided by, this is the 1242 into 1.6, and this is the 10 to the power 19 into 22. Okay, this is almost equal to 0.4 into 10 to the power 22 per second. So this is the 4 into 10 to the power 21 per second is the rate of incident photon on earth surface on the area of 1 meter square. Okay, understood? Next. Now a very important point, the Einstein explanation of photoelectric effect. When a radiation of frequency nu incident on the metal surface, the elastic collision takes place between the photon of the radiation and electron of the metal surface. In this elastic collision, electron absorbs either whole energy of the photon or none. If electron absorbs whole energy of the photon h nu, then three possible cases arises. Number 1, if absorbed energy h nu less than work function, then no emission of electron takes place. Number 2, if h nu is equal to work function of the metal, then emission of electron takes place with zero kinetic energy. And number 3, if h nu greater than W, emission of electron takes place with maximum kinetic energy h nu minus W. So look at this, K max, this is equal to half mv square, where v is the maximum velocity of photoelectron, this equal to h nu minus W. This equation is known as Einstein's equation of photoelectric effect. Now this relation can be written as half mv square, this is the h nu, and W is equal to, this is the h nu naught. So this is the h nu minus h nu naught. Again, nu is equal to c by lambda, so this can be also written as hc by lambda minus hc by lambda naught. This is the another equation of Einstein. Okay, this is equation number 1, this is equation number 2, and this is equation number 3. Look at this, we also know if V naught be the stopping potential, then K max, that is half mv square, is the EV naught. So look at this relation can be written as, look at this is the EV naught, this is the equation 4. This is the, look at this is the E V naught into H nu minus H nu naught. This is equation 5. And E V naught, look at this, E V naught, this is the AC by lambda minus AC by lambda naught. This is equation 6. Okay. This is the other forms of Einstein's photoelectric equations. Okay. If a graph is plotted between maximum kinetic energy of photoelectron and frequency of radiation, then this graph becomes straight line. Look at this. This is the half mv square. So this graph is like this. Okay, now the slope of the graph, look at this, tan theta, this is equal to h, because look at this, here half mv square, this is the h nu minus w, and look at this represents the w. Okay, now another graph, look at this, the another graph, look at this like this. So these two graphs, look at this, these two graphs are parallel because both have slope tan theta is equal to h. Okay, only they differs by their threshold frequency. This is the, look at this is the graph for one surface and this is the graph for another surface whose work function is like, look at this is the omega dash, and this is the threshold frequency nu naught, and this is the threshold frequency nu naught dash. Okay, so the graph between half mv square and nu is parallel to each other for different metal surfaces. Okay, now if another graph draw between the stopping potential V naught and the frequency of radiation, then this graph also straight line having slope. Look at this, if this is the E V naught, so V naught is the h by E into nu minus w by E. So look at this, here slope becomes h by E, here slope becomes h by E, and the intercept, this is the w by E and this is the w dash by E. Okay, so nature of graph between stopping potential nu naught and nu and maximum kinetic energy half mv square nu naught are almost identical, only they differ by their slope. Look at this, ncert 11.2. The work function of cesium is 2.14 electron volt. If a radiation of frequency 6 into 10 to the power 14 Hz incident on the cesium, we have to calculate maximum kinetic energy of the photoelectron, that is h nu minus w, and stopping potential and maximum speed of photoelectron. Now look at this, maximum kinetic energy of photoelectron, here k max, that is half mv square, this equal to h nu minus w. Look at this, h is the 6.63 into 10 to the power minus 34, nu is the 6 into 10 to the power 14 and 10 to the power 14. Now this into this is the joule, so it should be converted into EV, so it should be divided by the 1.6 into 10 to the power minus 19 minus W, that is 2.14. okay, this is the electron volt. Okay, now look at this, 6 into 6.63, so this is the 40, so 40 into 10 to the power, this is the minus 20 and this is the 1.6 and minus 2.14 electron volt. Now this is the 2.5 minus, this is the 2.14 electron volt, so this is the almost 0.36 electron volt. Now K max, so K max is the 0.36 electron volt. Stopping potential E V naught. Now now we have to calculate V naught. We know E V naught is equal to K max, so V naught is the K max by E, so V naught is the 0.36 electron volt by E. Now E cancel out, so this is the 0.36 volt. Now maximum velocity of the photoelectron. Now to calculate the maximum velocity of photoelectron, energy should be calculated in joule unit. So look at this. This is the half mv square is equal to 0.36 electron volt. So this is the 0.36. It should be converted into joule. 1.6 into 10 to the power. This is the minus 19. So look at this from here. V naught is equal to under root of 2 into, this is the 0.36 into 1.6 into 10 to the power minus 19 divided by 9.1 into 10 to the power minus 31. Okay, understood? Look at this. This is the 10 to the power minus 31 and this is the 19. So 10 to the power 12. So outside the root it becomes 10 to the power 6. So V is equal to 0.36, that is 0.6. Now 2 into 1.6, 3.82. So this is the 1.8 and this is the 3 into 10 to the power 6 meter per second. Okay. Now this is the 0.6. So this is the 0.36. So this is the 3.6 into 10 to the power 5 meter per second. Okay. Now ncert example 11.2. The work function of cesium is 2.14 electron volt. Find its threshold frequency and find the wavelength of radiation by which the stopping potential of electron is 0.6 volt. So here work function is given. We have to calculate the threshold frequency nu naught. Okay, we know the work function W is equal to h nu naught. Okay, understood? So here nu naught is equal to W by h. Look at this. Here 2.14 electron volt and h is equal to 4.14 into 10 to the power minus 15 electron volt into second. So look at this. Here 4.14 into 10 to the power minus 15 EV into second. EV cancel out. Okay. So look at this. Here 21.4 divided by 4.14 into 10 to the power 14 hertz. Okay. This is 5.16 into 10 to the power 14 hertz. Okay. Now stopping potential of electron is 0.6 volt. We have to calculate the wavelength of radiation. Here maximum kinetic energy of electron EV naught equal to hc by lambda minus, this is the 2.14. Now this is the 0.6 electron volt equal to hc by lambda minus 2.14 electron volt. Therefore hc by lambda, this equal to, look at this plus this. So this is the 2.74 electron volt. Now the value of hc is 1242 EV nanometer. So here lambda is equal to 1242 EV nanometer divided by 2.74 electron volt. This and this cancel out. Okay. This is the 454 nanometer. So wavelength of incident radiation lambda is equal to 454 nanometer. Understood? Next. Now ncert numerical 11.6. The slope of stopping potential and frequency graph h by E is equal to 4.12 into 10 to the power minus 15 volt second. We have to calculate Planck's constant. Now from this relation h is equal to 4.12 into 10 to the power minus 15 EV into second is the value of Planck's constant in electron volt second unit. Now matter wave. The total energy of the universe is constant and this energy remain in the form of radiation and matter. Radiation exhibits the particle properties. Okay, as nature loves symmetry, so de Broglie suggested that matter also has wave property. This wave is called matter wave. Now, wavelength of matter wave. The energy of photon of wavelength lambda is E equal to hc by lambda, where h is the Planck's constant and c is the velocity of light in the vacuum. Now, according to Einstein's theory of relativity, energy E is equal to mc square. Therefore, now if we equate this and this, we can get hc by lambda, this equal to mc square. Therefore, lambda is equal to h by mc is equal to h by p. Now, this formula of wavelength of photon is also applicable for matter wave. If a particle of mass m moves with velocity v, then its momentum p equal to m into v. So, wavelength of matter wave lambda is equal to h by p equal to h by mv. Okay. Now, wavelength of de Broglie wave in the form of kinetic energy, temperature and accelerating potential. We know the wavelength lambda, this equal to h by p, where p is the momentum of the particle. If the velocity of the particle of mass m is v, then p equal to mv. So here h by mv. Now the momentum mv can be expressed in the form of kinetic energy, and this is equal to mv equal to root under 2me, where E is the kinetic energy of the particle. So here lambda is equal to h by, this is the root under of 2me. Okay. Now if a charged particle Q accelerated with a potential difference V, then E equal to, this is the Q into V. Therefore, lambda is equal to h by root under 2mq into V. Okay. Now, kinetic energy of a molecule E equals to, this is the 3 by 2 K into T, where K is the Boltzmann constant and T is the Kelvin temperature. Now, from this relation, lambda equal to h by root over, this is the 2m into 3 by 2 KT. Therefore, this is the h root over of, this is the 3mkt. Okay. So look at this. There are four expressions for wavelength of matter wave. Here lambda equals to h by p. Here lambda equals to h by mv. Here lambda equals to h by 2me. And here lambda equals to h by 2mqv. And finally lambda equals to h by root under 3mkt. Okay. Understand? Now a numerical. Now look at this, a numerical. A proton having charge q, mass m, and an alpha particle having charge 2q and mass 4m have same momentum, same velocity, same kinetic energy, same temperature, same accelerating potential. Find a ratio of their de Broglie wavelength. Now in terms of momentum, the expression of wavelength lambda is equal to h by p. So look at this, here lambda p by lambda alpha. So look at this, here both have same momentum. So h by p is to h by p. So this is the 1:1. Okay. Now in terms of velocity, look at this, here lambda p is to lambda alpha. So here h by m into v is to h by, this is the 4m into v. So this is the 1:1 by 4. So this is the 4:1. Okay. Understood? Now in terms of kinetic energy, Look at this, in terms of kinetic energy, lambda is equal to h by root under 2me. So here kinetic energy h are constant. So here lambda p is to lambda alpha. So here 1 by root under m is to 1 by root under, this is the 4m. Therefore, this is the 1 is to 1 by root 4. So, this is the 2 is to 1. Okay? Understood? Now, next. Now, in terms of temperature, the de Broglie wavelength lambda is equal to h by root under 3 mkt. So look at this, have same temperature, so K constant, T also constant, H constant. So here look at this, lambda proportionate 1 by root under m. Okay, so this is the same ratio as that of kinetic energy. So here lambda P is to lambda alpha, this is 1 by root under m is to 1 by root under 4m. So this is the 1 is to half. So this is the 2 is to 1. Okay. And finally, in terms of accelerating potential, the de Broglie wavelength lambda is equal to h by 2m cube v under root. Here h and b constant. This here lambda p is to lambda alpha. This is, look at this, this is the 1 by root under 2m cube v is to 1 by root under 2 into 4m into 2q into v. So this is the 1 by, so this is the 1 by 1 is to 1 by root under 8. So this is the 2 root 2 is to 1. Okay? Understood? Next. Now example 11.4. We have to calculate the de Broglie wavelength of an electron having velocity 5.1 into 10 to the power 6 meter per second and a ball of mass 0.150 kg moves with velocity 30 meter per second. Now first of all, the de Broglie wavelength of matter wave. Look at this, here lambda is equal to h by, this is the m into v. H is the 6.63 into 10 to the power minus 34 joule second, and this is the this is the 9.1 into 10 to the power minus 31 and 5.4 into 10 to the power 6. Okay, look at this here. Now look at this, minus 31 minus 34 minus 3, and this is the 6. This is the 10 to the power minus 9. Okay, now this is the 6.63 divided by 9.1 into 5.4. This is the meter. Okay, and this equal to 0.135 into 10 to the power minus 9 meter, and this is the 0.135 nanometer. Okay, now we have to calculate the wavelength of this ball. Here lambda dash, look at this, here h is by m dash v dash. So here 6.63 into 10 to the power minus 34. Here mass is the 0.150 into velocity is the 30. So look at this, this is the 6.63 into 10 to the power minus 34, and this is the 4.5. Okay, so this is almost 1.47 into 10 to the power minus 34 meter. Therefore, de Broglie wavelength of a particle on Earth's surface is very, very small. Okay, now example 11.5. Electron, proton, alpha particle has same kinetic energy. Which one has shortest possible lambda? Now, in terms of kinetic energy, the de Broglie wavelength lambda is equal to h by root under 2me. Look at this, the kinetic energy is same, so lambda proportionate 1 by root m. Look at this, the mass of electron is least of all three. As mass least, so its de Broglie wavelength is maximum. Okay, therefore the de Broglie wavelength is least as alpha particle has maximum mass. So alpha, lambda alpha is the least wavelength than the proton or electron. Okay, look at this, the ncert 11.16. The wavelength of electron and photon both have 1 nanometer. We have to calculate the momenta of electron and photon, energy of photon hc by lambda, and kinetic energy of electron ee. Okay, now first of all look at this, lambda is equal to h by p. Okay, so look at this, both have same momenta, p is equal to h by lambda, here lambda same, so lambda here 6.63 into 10 to the power minus 34 divided by 1 nanometer, that is 10 to the power minus 9 meter. So this is the 6.63 into 10 to the power minus 25 Newton into second. Okay, now energy of photon, look at this, here lambda given, so energy of photon, this is the hc by lambda. Now hc is the 1242 eV nanometer, and this is the lambda is 1 nanometer, therefore nanometer cancel out, therefore 1242 electron volt is the energy of photon. Now kinetic energy of electron, we know the lambda of electron is h by root under 2me. Okay, so here lambda square equal to h square divided by 2me, therefore the kinetic energy of electron E is equal to h square divided by 2m into lambda square. Therefore kinetic energy of electron EE, this equal to 6.63 into 10 to the power minus 34 whole square divided by, this is the 2 into mass is the 9.1 in 10 to the power minus 31, and lambda, this is the 10 to the power minus 9 whole square. Okay, this is the 6.63 whole square divided by, this is the 18.2, and this is the 10 to the power minus 15, this is the joule. Okay, now look at this 6.63, that is almost 20 by 3, so this is the 400 divided by 9 into 18.2 into 10 to the power minus 15 joule. Okay, now wavelength of electron, look at this, an electron is accelerated of potential difference v, so its kinetic energy half mv square, this is equal to E into v, therefore v is equal to root under of 2ev by m. Therefore lambda is equal to h by m into v, so h divided by, this is the m into root under of 2ev by m, therefore here lambda is equal to root under 2mev. Okay, therefore de Broglie wavelength lambda is equal to h by root under 2mev. Okay, in SI system, look at this, this is the 1.227 into 10 to the power minus 9 divided by root under v, where v is in volt unit, so this is the 1.227 nanometer by root under v. Okay, now example 11.7, we have to calculate the wavelength of electron accelerated with potential difference of 100 volt. We know the wavelength of accelerated electron, this is the 1.227 nanometer divided by root under v, where v is in volt unit. Now here accelerating voltage is 100 volt, so here 1.227 nanometer divided by root under 100, so this is the 0.1227 nanometer. Okay, understood? Now next, Davisson Germer experiment to prove the matter wave. Look at this, electron beam are incident on nickel crystal from a cathode. This electron beam scattered in different direction. The intensity of scattered electron is measured by a detector D. The intensity of a scattered electron different angle of scattering, and intensity also depends on the accelerating potential of the source from where electrons are coming. If the electrons are accelerated with the potential difference of 54 volt at the angle of 50 degree scattering, the intensity becomes maximum. This maximum intensity is obtained due to constructive interference of electron beam coming from two equally spaced layers of nickel. So using this phenomena, if we apply Bragg's law, we can obtain the wavelength of electron lambda equal to 0.165 nanometer. Now from de Broglie theory, the lambda dash equals to, this is the 1.227 nanometer divided by root under 54. So this is almost 0.167 nanometer. Now this is the experimental value and this is the theoretical value. These are almost same. Therefore the electron exhibits the wave property. Okay, many thanks for watching this video. This video will be extremely helpful for your board exam, NEET, main and advanced. Please like, comment and share the video. And if you are new, don't forget to subscribe my channel to get the new concepts in physics. Okay?